Hi there. So this video is on organizing data, and it references section 1.1 from your textbook, but I feel like that section is really rich in a lot of background knowledge and sorting everything out. And so I'm going to break this into 3 videos, um, just because some sections are very short, but this one I feel like is a little bit more densely compacted into one section. So we'll talk about percentages, fractions, decimals, and degrees. So we'll toss in degrees into these computations. We'll interpret and create frequency tables and relative. So the difference between just a raw frequency count and the relative frequency count relative to how many total we have. And we'll distinguish between 2 different types of data. This isn't specifically in this section, but it's implicitly there. So we might as well say what it is and get that vocabulary started, in my opinion. And then we're going to create bar graphs and pie charts, and we're going to use them. So when it comes to example 1, we're actually going to use this type of bar graph. It's not exactly, it's called a stacked bar graph, but nonetheless, let's read it, use it, interpret it. Okay. So this projections of jobs and education requirements. Oh, looks like I have a typo right there. Forgot the space. This was actually published before 2018. I want to say in 2012 maybe. But in it, they made the claim by 2018, 63% of jobs in the United States will require some form of college education. And I remember this being a pretty big deal because a lot of people were then being told, like, hey, push college or push some sort of higher credential. And there was a lot of pushback, like, why would we do that? I mean, not everybody should need to go to college, which is actually true. But they were making data-informed decisions, and so let's do that too. Okay. Question 1 says, what percent of jobs required a high school diploma or less in 1973? I'm going to zoom in on these numbers. Okay, so let's take a peek at 1973, and it looks like this orange band is people who have earned, they've either graduated from high school and gotten their diploma, or maybe they got their GED, or basically a high school equivalency in this orange category. And then this blue category at the bottom is high school dropout, so maybe they pursued different interests. But nonetheless, this would be high school diploma or less. Higher than that is some sort of, so some college might be a certificate or an associate's, or, maybe you went to beauty school. I don't know. Anyway, just kind of certificate. So high school diploma or less in 1973, well, that would be this 40% in addition to this 32%. So 73% of jobs required a high school diploma or less in 73. And then what about in 2007? Well, if we look at, so this was 1973, and then 34 years later, we look at 2007, and we notice that's 30% in addition to 11%. So 41% of jobs required a high school diploma or less in 2007. That's a huge change in the market. Like, what job am I going to get? Well, there used to be a lot of industrial jobs and not as much services. And now there's been a shift in the United States. I believe it's, the jobs in the United States. And that is a pretty significant change, I would claim, in the job market. And then it says, what was the projected percent of jobs requiring a high school diploma or less in 2018? Okay, so now we're going to go back up here to 2018, and this was a projection because remember, they had published this before 2018. This was the data they were running with, and then they were using a model to predict this percentage. So it looks like 28% in addition to 10%, that's 38%. Okay, so they predicted based on previous data that, and previous data and maybe and perhaps other variables when it comes to this too. What was the projected percent of jobs requiring a high school diploma or less? Well, 38. Okay, it ended up being, I did a fact check on this, ended up being 36, so actually less than what they projected. But you see this trend of what portion of the jobs on the market actually require, your GED or high school diploma or equivalency or less, and then how much of the job market requires actually more than just your diploma or your GED. So we see what's happening in the market just from this one stacked bar graph. Okay. Question 4 says, how does having this information help you make informed decisions? Well, I'm going to leave this one blank because really this is for a student to fill in. But I know that my students from the past have traditionally said something like, well, that's why I'm here, lady. I know that there are fewer jobs for me, and so the competition is more fierce, and so I'm gonna come here and come to ECC and get some kind of certificate or an associate's, or you know what, if I come to ECC and I figure this is kind of my thing, then maybe I'll do more, whatever. I'm here to try to figure out what kind of job I can do for the rest of my life. Well, ish. Actually, people tend to change their jobs from time to time, but still, you're at the right place to figure out what you don't like and hopefully make yourself more competitive in the market to get a job. So, how does this help you make informed decisions? Well, it kind of tells you why it feels so competitive. So when I was an undergrad, my first year of college, I actually tried to get a job at a video store. So I was like, I shouldn't need too many skills, like show up on time, make sure I don't screw up money, keep things cataloged. And they rejected me. I was like, why? How could I get rejected for a job that I thought required less skills than working at a fast food place, which I had been doing? And the reality is that they knew I was in college, and they had people applying for the job who didn't have college credentials or going into it. And so they were like, nope, you'll be fine. And we're going to give this job to someone else who is going to stick around for longer because they don't have they're going to stay. So I think it's important to know, what kind of decisions you can make based on what you know. So, data. So to me, data is a fact or proposition used to draw a conclusion or make a decision. So, fact. I'll just put a fact. Okay, so, and I say this, there is, I believe that, you know, a lot of people view data and they're like, oh, so boring and dry. It's just all these numbers and all these like letters, who knows what, whatever. It's just so boring and dry. But the reality is that we draw a lot of conclusions and we make a lot of decisions. And sometimes we can base those decisions in facts and what we can check on. And sometimes we just go with our feelings, which has a little more risk, in my opinion. So when I think about data, I actually don't really think about it as being dry and boring. I think about it as being just really informed and decreasing my risk in data decision making. So, or in decision making. I've given it a tag, which is data decision making, but still. So this is what data is to me. Let's look at example 2, blood types. 24 Army inductees were tested for their blood type. The results are in this table. Now, I want to give a quick shout out to all of the people who are not necessarily gender binary, and in order to tell you, but I must say that the U.S. military actually does break this into 2 categories, males and females, and there are very specific details on how they separate and base their gender identities. Now, this is going to be different in the military versus when people are born, versus how you give your own gender identification. And so I just wanted to put in here how this, how these categories were actually decided upon in terms of collecting data. Okay. Now, that being said, we're going to go ahead and use theirs as we fill in more data types. So the results are in this table. Make another table for this data, this time using percentages instead of the raw number of counts out of 24, which is called the frequency. Like, how frequently did you get a male of type A blood? Okay, so let's do that quick. Percentages. So when I think about the percentage, I think, okay, I'm going to go up here, and this first, I don't know, box, cell, location, whatever, is males of type A out of these 24 Army inductees. And up here, I see that this is 4 out of 24 inductees. So this right here is 4 out of 24. And if I pull out my handy calculator and I go 4 out of 24, and so 4 out of 24 was approximately I don't know, I guess we can round to 0.17, which is a lot of rounding because there's plenty of decimals and precision here to go with. And that converted into a percentage would be 17%. Okay, so here we see this is approximately 17%. Okay, I'm going to show the work for one more, and then I'm actually going to fill in the entire shebang. So now if we look at the number of females of type A out of the 24 Army inductees, I look at, okay, so this cell is 1 out of 24, and 1 out of 24 is approximately 0.04, which is 4%. Okay, so here we go, 4%. And now if I look at the total, This would be 5 out of 24. Or I could just look at the total of type A and notice that this is 17 and 4, and that should be 21. So 21%. Okay, and now I'm going to go ahead and fill in each one of these as well. Males type B, that would be 5 out of the 24. 5 out of 24, I got approximately 21%. Okay, and 2 out of 24, which simplifies to 1 out of 12, got approximately 8%. Total those up, I see 29%. 29% is 7 out of 24. Type AB, 4 out of 24. I feel like we've already done that, 17%. 0 out of 24, that's nice, 0%. Total, 17%, about. Type O, 7 out of 24. 7 out of 24, I got approximately 30%. 1 out of 24, well, that's half of 2. I bet it's going to be 4%. Approximately 4%, total that, 34%. Okay, let's see. I would like to mention that 8 out of 24, so immediately I notice right here, so I'm going to put a star. 8 out of 24 is, let's see, this scales down. I noticed that you can scale down the numerator and denominator by 8 and glue 8 pieces into one, but if I were working this out by myself by hand, I probably wouldn't actually divide by 8 right off the bat. I probably would divide by 2 and scale down to 4/12, and then I would divide by 4 and see that that is 1/3. And I know that when you put that on the decimal or in the calculator, 1/3 is equal to 0.3 repeating, so 0.333333333 forever and ever. And if we turn that into a percentage, that will round to about 33%. So I noticed that there must have been some error here based on rounding. This 30% with more precision maybe was 29.2, and so it got rounded. Let's see how much rounding happened. Let's take a peek at that really quick. So this 30%, 7 out of 24, okay. I feel like I have mistyped here. This should not be a 30. That should be a 29. Okay, found a mistake. I made a mistake in my calculations. This should be a 33. Got it. Okay, sorry about that. So this should be a 29%, and that should be a 33. Okay, found a typo in my own notes here based on recognizing that 8 out of 24, I think, is a third. So then we go ahead and we total all of these up. So the male, so 20 out of 24, that is about 83%. And 4 out of 24 Army inductees being categorized as female, that's approximately 17%. And then this should be the overall total, 24 out of 24 should be 100%. Okay, so number 2, what should always be the total in the bottom row? Okay, so if we look at this, and here's our total, but this bottom row, and we add all of these together. So let's go 21%, 29%, 17%, and 33%. Hopefully that adds up to 100%. Let's check that. Okay, so 21%, 29%, 17%, and 33%, 100%. Okay, so 100% of people have to have are of type A, type B, type AB, type O blood, basically is what that is saying. So in this bottom row, these should really total to 100% of everyone who got their blood type tested. Number 3, what should always be the total in the rightmost column? Okay, so basically if we look at the right here, 83% plus 17% adds up to 100%. And what that is saying is this: if we go and we classify individuals based on the United States military identification of female and male genders, then you should get 100% of people because they have put them into one of these two categories. Sometimes these totals do not add up to 100%. Why is that? Well, I can see right off the bat that we actually rounded quite a bit. So every number in this table ended up being rounded. If we had rounded differently, and I don't mean incorrectly. When I say rounding, I mean we rounded to the whole decimal, or I'm sorry, a whole percentage, which ended up working out in our favor because everything added up to 100%. But if we had more precision based on rounding up and down, sometimes this doesn't actually add up to a perfect 100%. Maybe it adds up to 99.9% or 100.2%. And that's all because of rounding. So sometimes they don't add up to a perfect 100%. Rounding. Rounding causes error. Okay, you've got to pardon my little boo-boo here. I actually am quite clumsy. I ran into the countertop. That is just plain and simple. Like, I was working in the kitchen and then bam. So, anyway, random. I'll focus now. Based on this data, what is the most common blood type? All right, let's take a peek. So if I look here, I got 21% versus 29 versus 17 versus 33. Type O. And we could have looked up here and just looked at the raw frequencies too, 5, 7, 4, or 8. 8 was the most frequent in terms of blood types. So type O, most common. Why might the Army need to know this? Well, when I look at this data, I'm not entirely sure why this data table included the gender identifications, unless it, perhaps that speaks to something like quantity of food you need on a base, or number of boots in size whatever. Insert, the typical boot size for an individual based on these two categories, right? So it's possible that breaking things down by genders helps them anticipate what kind of goods they would need in order to house and treat these people well. And certainly when I think about the blood type, immediately I think, well, they might get hurt and they might bleed, and so they might need blood, and so we should have blood on hand. And if you look at it, we should have twice as much, almost, well, according to this raw data, right? We should have twice as much type O as we have type AB, because it's just apparently more popular in this round of inductees. So I think, why might they need to know this data? Take care, soldiers. That's why I think they need this data. Basically, in order to make sure they're taking care of the soldiers who, have decided to take a risk upon themselves to protect our freedoms and liberties. It's really interesting at a time like this to talk about, our military and its protection of our liberties. So, anyway, food for thought. Make a pie chart using this data. Okie dokie. If I'm going to make a pie chart, I need to bring back all of that, write down each one of my categories here. Type A was about 21%. Type B was approximately 29%. Type AB was about 17%. And type O was about 33%. Okay, here we go. So I'm going to start by drawing a circle, and I don't know. That's about as good as it gets in terms of a perfect circle for me. And that's about the center. Whatever. It's a little bit lopsided, but what are you going to do? The first thing I always do is I actually cut this into quarters, because that is the easiest thing for me to approximate. So, yeah, they're not perfect, but those are about a quarter. And I think of a quarter as 25%. Okay. Which means I'm kind of going to go a little bit under that, a little bit over that. I've also noticed in this data something interesting is happening. 21% plus 29% is exactly 50%, and 17% and 33%, that's another exact 50%, which is half of this. So that actually helps me in terms of predicting and making good judgment. Use good judgment for sizes. This is what I mean by that statement. So let's see, 21 versus 29. And I know that this is an entire 25%, this portion right here. So if this is an entire 25%, then, let's see. This is 4% away from a perfect 25%. That's not a lot in terms of proportionality. So I'm going to just make this something like that. Okay, maybe even a little bit smaller, but I'll leave it. Okay, so type A, 21%, is the smaller of these two. Okay, so I'm going to erase my quarter. I used it as a reference, but now the smaller of these two, right here. So this sector, I'm going to label as type A, which was about 21%. And type B is the rest of this half, because I knew that adding them together gives 50%. So this is type B, which was about 29%. Okay, done. now I look at type AB versus type O, and let's see, one half of 1/4, which by the way is an eighth, but a half of a quarter would be half of 25%, and that's 12.5%. Okay, so if I were to split this in half, about like that-ish, then 17% would be just over that. What is that? Increase this by 4.5%, and you would be there. So type AB is actually just a little bit bigger than this right here. So I'm just going to make it look like that. Okay, so, and now I can get rid of my reference lines. Type AB, about 17%. And last but not least, actually last but the most, is this sector. And this sector was type O. And that was approximately 33%. Okay. I just thought to myself, I don't even remember. I know that one of these blood types is the universal blood type, where that can donate to any of the other blood types, and I don't remember which is which. If so, whatever the universal one, you'd probably want to have more of that on hand. But again, that is that's out of my purview. Like, take biology or whatnot in order to learn about that. Frequency. Okay, here we go. So frequency is a raw count of how many. So frequency, count of how many. How frequently did that happen? How frequently did type A happen? Okay, well, I can tell you that. Type A happened 5 times out of these 24. Relative frequency. So I just said out of, and that to me is relative. So the raw count of type A was actually 5. The relative frequency of type A, now that's different. So this is a ratio, a fraction, or a percent of how many out of the total. Okay, so when I think about this as a ratio, fraction, or percent, I think this is actually the count of how many compared to the total. For example, this was 5 out of 24. So that would be a relative frequency. How many? 5. Well, relative to how many were actually inducted at this one particular moment, well, out of 24. And then when I think about the pie chart is categories of data drawn as sectors of a circle. So, okay. Categories of data. Drawn or represented. Okay. Drawn as sectors of a circle. That are proportional in size to their relative frequency. So proportional size to their relative frequency. Okay, so the bigger the percentage, the bigger the piece. And I also wanted to mention that this circle represents the whole. So this is the entire induction of these Army inductees. I don't even know what to call them. Anyway, people who just entered. And so the complete circle right here is really the whole. So 21% of all of the 24 inductees. Okay, so we started this with a couple of examples about using data, and we used a table, and we also organized things into, we repeated the table but within percentages, and then we went ahead and drew one of these pie charts as, I see I have a little boo-boo here, whatever, as representation of a portion to the whole. So there were fewer of these in the whole induction versus type O in the whole induction. In the next example, in the next couple of examples, we're going to really dig in and have more data and do a better job of refining this process.